So just like with the area, your volume is going to work very similarly. And so now I'm going to do an example that puts everything we just talked about all together. Okay, so here we have a region described for us, and we want to find the area and the volume of f of xy equaling e to the x plus y over this particular region. Okay, now one thing to keep in mind, this is really two separate problems. For the area, remember we don't actually need the function, we just need the region. And then for the volume, we need both. Okay? And so here, again, the first thing I'm going to do in this type of a problem is I'm going to start by figuring out again what my equations are and figure out which order of integration I want to do. Okay? So here, let's start by finding our equations. So nicely, if we look at this, we can see for this line over here, the slope is just 1, and the y-intercept is 1. So this line here is just y equals x plus, I said that wrong. The slope is negative 1, and the y-intercept is 1. So y is going to equal a negative x plus 1. And then over here, we can see the slope is positive 1, so rise over run, and the y-intercept is 1. So this one is going to be y equals x plus 1. And again, we can check those. At negative 1, we get 0. At 0, we get 1. Here at positive 1, we get 0. At 0, we get positive 1. Okay. And of course, this line down here, this is just y equals 0. Okay. So again, the first thing I want to do is figure out which order I'm going to integrate. So again, I want to look at vertical lines versus horizontal lines. And the first thing that should be very apparent is if I try to do a vertical line, the problem is my upper curve is going to change depending on which side of the y-axis I'm on. So here, I really do want to integrate this direction first and then worry about integrating the other direction. Okay? So here in my integrals, I'm going to want it so that x is first and then y. And if I look at my limits on x, they're going to start over here at the y equals x plus 1. Again, I need it as an x equals, so that's going to be a y minus 1. And it's going to stop over here at y equals negative x plus 1. Again, putting it in terms of x, says x is going to equal negative y plus 1. Okay? From there, I'm going to squish this to the y-axis to figure out what my limits in y are. So squishing that, and I can see that my imprint is going to be from 0 to 1. Okay? So there's kind of the setup for my integration. Now let's actually set up our integrals and solve them. Okay? For the first part, my area, well, we've basically already set it up. Okay? Again, we don't need our function in there, so the integral from 0 to 1, integral from y minus 1 to negative y plus 1 dx dy, that'll give me my area. Okay, so I'm going to integrate the inner piece first. So integral of dx is just x, and I'm going to integrate that from y minus 1 to negative y plus 1 dy. So my upper limit minus my lower limit is negative y plus 1 minus y minus 1. Again, I can clean that up before I integrate again. So minus y looks like a negative 2y. The 1 plus 1 looks like 2. So there's my one variable integral. Okay. From there, integrating with respect to y, we'll get a negative y squared plus 2y, integrating from 0 to 1. At my upper limit, I can plug in. I'm going to get a negative 1 plus 2. At my lower limit, we can see that's going to go away. We'll just get 0 and 0. So my area here is just going to be 1. And again, we can check this. Nicely, this is a nice geometric region, so we know that area is base times height. 1/2 base times height. So my height we know is going to be 1. My base is from -1 to 1, so that's 2. And 1/2 of that we can see is going to just be 1. Okay, so we know we did that right. Okay, so let's look at the volume. Now again, what the volume is saying is I've got this function e to the x plus y up here in the z-plane, and it's being imprinted over this region. And so we're thinking of the distance between that function and the region is the height times that area. So that'll give us our volume. So here, our volume, again, the difference between these two formulas is now I'm going to plug in my function. So same limits we just had. I'm going to put an e to the x plus y in here, integrating dx and then dy. Okay. So integrating in that innermost interval first, I'm going to integrate with respect to x. So the 0 to 1 just gets carried down. Antiderivative of e to the x plus y. Well, that's just e to the x plus y. Okay. Again, if you don't see that right away, let u equal x plus y. Our du is just going to be dx. So again, we're not going to divide out by anything. We're going to evaluate this from y minus 1 to negative y plus 1. So plugging in at our upper limit, we're going to get an e to the minus y plus 1 plus y, minus, at the lower limit, e to the y minus 1 plus y. So remember, you're plugging in for x there. Okay. Again, we can simplify. So 0 to 1, simplifying here, the y's cancel, so we're just looking at e to the 1 minus over here, e to the 2y minus 1. Okay. Now we're going to integrate. Now here you got to be a little careful, this one's kind of tricky. E to the 1 is just a constant, so when we integrate that, we're going to get y times e minus over here, this one you need your u sub again. So here we're going to get 2y minus 1 being our u, which means we're going to end up with a 1/2 e to the 2y minus 1. And we're going to integrate all of that from 0 to 1. So at our upper limit, plugging in for y, we're going to get e minus 1/2 2 minus 1, which is e to the 1. I guess I don't really need to write the 1's in there. Minus at the lower limit, when y is 0, we get 0 minus, again, be careful, we'll get a 1/2 e to the negative 1. Okay. And so now putting this all together, e minus 1/2 e is 1/2 e minus a negative, so plus 1/2 e to the negative 1. There's our volume for that function. Okay. And so for some of these problems, you're going to be asked to do things very similar to this, where you're given a region, whether it's written out in words, meaning I give you the equations but not the picture, and you have to come up with the picture, or ones where you're given the picture like this and you have to figure out the equations, and then some function so that you're asked to find both the area and the volume. And you should be able to do both of those things for any of the regions we're going to give you. Okay, so now that you thought you were done, we have one last thing to do in this chapter, which means one last thing to do in this course. And that is to talk about one last application of our multiple integrals. And that last application is our average value. So if you remember back in chapter 7, we talked about average values of a function, and we also talked about moving averages. We're not worried so much about moving averages for these. We are thinking average value of a function, though. And so if you recall, the average value of a function, we said was f bar equaling 1 over b minus a, the integral of a to b, f of x dx. Okay? And so here, the main difference, if I want to find the average value of some function over a region, if I expand this to multiple variables, what this is saying is that here, what we're going to do is for our average value of our function in the multiple variable sense, it's going to be 1 over the area. So again, we're expanding by one dimension. So here we were looking at a length. So now we have an area. And here we had our area. So we're going to expand that to the volume. I'm going to write it this way. And then I'm going to put the real formula here. So it's going to be 1 over our double integral dy dx, or dx dy, whatever that is, times the double integral of our function dy dx. Okay? So here we're going to do pretty much the same thing we just did in that last example. The only difference is once we get both the area and the volume, we're going to combine them together to get our average value. Okay? And so in this case, again, the first thing I'm going to do is I'm going to start by getting my equations. So if we look at this, we've got basically a diamond, and if you'll notice, if you notice, the region is very similar to the one we just did. So again, if I look at my equations here, this one is going to be y equaling a negative x plus 1. This one here is our y equaling x plus 1. Over here, our slope is positive 1, and our intercept is negative, so x minus 1. And over here, our slope is negative, and the intercept is negative 1. Okay, so we've got our equations. Now, it almost looks like we're not going to be able to do this kind of like we did last time. Because if I look, if I try to do vertically, I have two different values or equations for my upper and lower, but I also have two different equations for my right and left. But this is where symmetry is going to play a big part. And I can see pictorially, but also with my equations, the equations on the bottom half are exactly the mirror image of the equations on the top. So I can use symmetry to actually get my area in this one. Okay? So here, I'm going to start by getting my area function. My area is going to look like the integral. Again, we're going to integrate dx dy. Actually, here it doesn't matter. We can pick because we can also do left and right. I wrote dy dx first, so let's do that one. So if I look at my y's, the way to do this, I need the y's to be so that the vertical lines work. And the only way that's going to work left and right is if I use one of the four regions. Okay? Because here if I do, or I can even do two of them, top and bottom. I just can't go across the y-axis. So here, if I look at it this way, my curves are going to start at x minus 1, and they're going to end at negative x plus 1. Okay? So there's the x minus 1 and the negative x plus 1. And if I look at my x's, so again, if I squish this to the x-axis, I can see that the imprint there is going to be from 0 to 1. Now there we're not quite done, because if I look at that, that doesn't quite cover the entire region. Okay? That's only going to cover from the y-axis over to that point. So again, using symmetry, I know that my area is going to be twice that. Okay? I have two of those regions. So here, we can go ahead and integrate. And even though I've got that 2 there, I can integrate it the exact same way we did the last one. So I'm going to start with the inner piece, which is y, and I'm going to integrate from x minus 1 to negative x plus 1. Evaluating at my upper limit minus my lower limit. So I see I get a negative 2x plus 2. From there, I'm going to integrate with respect to x. Again, the 2 just gets carried along. So integrating here, it looks like a negative x squared plus 2x. And I'm going to evaluate that from 0 to 1. At my upper limit, I can see that's going to be a negative 1 plus 2 minus at the lower limit, which nicely is just 0. Okay, so evaluating, I see my area of 1, and if you remember from the last example, that was exactly what we wanted. But now I'm going to double that, so my total area is going to be 2. Alright, so now that I have my area, I need to go ahead and find my volume. Again, my setup here is going to be very similar. So my V is going to equal 2 times the integral from 0 to 1, my integral x minus 1 to negative x plus 1 of my function, which in this case is x squared plus y squared, and I'm going to integrate dy dx. Okay? Same thing, start at the innermost integration. So here I'm going to integrate this with respect to y. Again, remember x squared is constant in this case, so I'll get an x squared y plus a 1/3 y squared. Sorry, 1/3 y cubed. And I'm going to evaluate that from x minus 1 to negative x plus 1. Okay, plugging in at my upper limit, I'm going to get x squared times the negative x plus 1 plus 1/3 of that same thing cubed minus at the lower limit, we'll get an x squared times an x minus 1 minus a 1/3 of that quantity cubed. And here I would definitely recommend cleaning up before you continue on. So expanding, again, definitely want to clean it up before we keep going. So expanding this, we're going to get a negative 8/3 x cubed, 4x squared minus 2x plus 2/3. We're going to integrate that with respect to x. So integrating, we'll get x to the 4th over 4, which looks like a negative 2/3 x to the 4th, plus 4/3 x cubed. Squaring that, we'll get a minus x squared plus a 2/3 x. And again, all of that is multiplied by 2 and evaluated from 0 to 1. So at our upper limit, we'll have 2 times negative 2/3 plus 4/3 minus 1 plus 2/3. At our lower limit, subtracting, notice everything there is going to go to 0. Okay. From there, simplifying, our 2/3 are going to cancel out. So we'll have 4/3 minus 1, which is a third, times 2, which looks like 2/3. Okay, so there's our volume for this. Now again, we're not quite done because we want the average value, which says I need to take my volume and divide out by my area to get my average value for this region. So, my f bar for this particular function is going to be 1 over my area times my volume. And so here we can see when we work that out, our average value is just going to be a third. There is the last concept that we're going to talk about in this course. Again, for what you're going to be expected to do on the homework and the web assign, you should be able to find areas and volumes separately. You should be able to, given a region, set up your integrations. Given some integrations, you should be able to sketch the regions. So we didn't exactly do examples of that, but the idea is exactly the same going backwards. And you should be able to find some average values of functions. Okay. On an exam, you are likely going to see one problem that involves all of what we just did here. So there's going to be at least one average value problem where you're going to have to set it up, be able to find the area and the volume, and be able to calculate it. There are going to be some that are just going to relate some of the concepts we've talked about. So maybe I'll give you a region like this and say, give me a one variable integral that will give me the area. Part B would be something like, give me a two variable integral that will give me the area. Okay? You may not actually have to solve it, but you should be able to set those things up. And so you'll be asked to do a couple of those in your exam as well.